Hello student, in this video I am going to discuss about a very small topic that is about homogeneous coordinates. So suppose here you can see a point xy can be written in homogeneous coordinate as xh, yh, h, and the homogeneous parameter h is non-zero value such that y equal to yh by h. So that is the relation with the homogeneous parameter. We can then write at any point xy as hx, hy. Okay, as like this you can put as you can write here also x equal to s of x of h by h. So and this equal to y into h equal to y of h, okay, and this will be equal to x h equal to x of h. So here this equation or this point can be written as this, because by transferring the xh value as xh or yh value as hy or yh comma h. So any point can be written as this, where h is the homogeneous parameter, and conveniently we choose h equal to 1 so that it becomes xy becomes x comma y comma 1, because if you multiply 1 with x it becomes x, 1 with y it becomes y, and comma 1. That is the homogeneous parameter. We can convert any point to homogeneous coordinate by introducing a homogeneous parameter using such equation, because h is a non-zero value, or you can say homogeneous parameter is a non-zero value. So why homogeneous coordinates? Because we know that we can do the basic transformation of 2D coordinates in generic way also. Then why do you need homogeneous coordinates? Mathematicians commonly use homogeneous coordinates as they allow scaling factors to be removed from the equation. We will see in a moment that all of the transformation we discussed previously can be represented as 3 by 3 matrix. So whatever we have discussed in the previous video about transformation, that three transformation, those are translation, scaling, or rotation. Those are represented as in the previous video in 2 dimension or 2D matrix. Here using homogeneous coordinate we can represent that matrix in 3 by 3, and also we can remove the scaling factors from the equation. So now we will see how it can be done. Using homogeneous coordinates allow us to use matrix multiplication to calculate the transformation extremely efficient. That is the point. That is the main point. Using homogeneous coordinate allows us use matrix multiplication to calculate transformation. Become more easy. So if we convert the previous equation into homogeneous equation, it will be like this. combining the geometric transformation into a single matrix by 3 by 3 matrices. Expand each 2D coordinate Expand each 2D coordinate and to 3D coordinate with homogeneous parameter. Here you can see this is the equation for translation. If we multiply, here you can see x dash will become equal to 1 into x, that is the multiplication, and 0 into y 0, tx into 1, that is equal to x plus t of x, and y dash will be equal to 0 into x 0, 1 into y plus ty into 1, that is ty, and if rest of them 1 will be almost equal to 1. For this 1 will be almost equal to 1 if we multiply the matrices. So by putting in a 3-dimensional matrix or transforming the whole scenario in this, or using homogeneous coordinate, if we create this scenario, then multiplication becomes easy and it brings or it creates the same equation as like previous. Just here one point is used, that 1 here and 1 also here, and also in this translation factor matrix also this has been introduced. So you can see these ones are introduced to create the homogeneous coordinate. Same like here also, this is for rotation matrix. If you multiply in the same way, you will find the previous equation of rotation for any point with respect to origin. So again, this one is about scaling. This is also, if you multiply, suppose x dash equal to, here you can see sx into x into x multiply, and 0 into y 0, 0 1 to 0. So this is the equation for x dash, and y dash will be equal to 0 into x 0 plus sy into y, and then 0 1 into 0, and 1 will be equal to 1. So again we can get the transform point after applying the scaling factor matrix with the original points in a homogeneous coordinate system after placing them or arrange them in this equation of 3 by 3 matrices. So that is the useful of homogeneous coordinates. Again, same thing can be done like in case of inverse translation. So if you want to do inverse translation, you just need to put the negative. And again, here also, to rotate inversely, you just need to put the, here you can see in the previous slide, this was positive, negative, positive, positive. But here this is negative only, rest of them are positive, because that thing comes here, or you can say sine of minus theta is minus theta. That is why cos of minus theta is plus theta, plus cos theta, and this was already minus, so my sine of minus theta is minus, then it becomes plus, and cos minus theta is plus cos theta, and sine minus theta equal to minus sine theta. So this is the reverse rotation, and just using this matrix we can apply the rotation in reverse way having the degree value. And again the inverse scaling is in this way. So just applying these matrices, multiplying with the given points, we can obtain the transformation value. So that is why using the homogeneous coordinate, it can be very efficient and useful while calculating the values. So here you can see, so basic 2D transformation equations are like this. Here one thing again added, that is shear. Shear is like shear. What is shear? Try to understand it. That is your homework. Okay. So that is all about in this video. In the next video we are going to discuss about geometric transformation in three-dimensional space. So if you have any confusion about whatever I have discussed in this video, then let me know. We'll try to resolve that over Google Meet. Thank you.